Hello, ENGR ampersand 214 engineering statics students. This mini lecture is an example about what you can do with the principle of R cross F to determine moment about a point. So in this example we have a what may not look like it on the diagram, but is actually a circular piece of rod, and it's embedded in some kind of wall or fixture that's attached to the z-axis. Here's the k-hat axis. We have a coordinate axes here, I hat, j hat, k hat. And there is a rope attached to it at point B. The rod is attached to the wall, we'll say at point A here on the k-hat axis, and the rod is laying in the YZ plane or the JK plane. So it doesn't have any bit of itself that is extending out into the along the x-axis. So it's all in the YZ plane. But there is a rope attached at point B on the rod, and that rope is attached to a point C here, which is at z equals 0 and is at x equals 6 and y equals 6. So the two dashed lines here are 6 over in the y direction and 6 out in the x. We're told that the radius of the circular rod is 4 meters, which means the distance up at point A is 4 meters because it's on one part of the circle, and our angle theta here that defines point B, very important, defines point B, is 45 degrees. And we're told that whatever is holding this rod in place over here on the wall, maybe it's embedded in a pillar or something like that, regardless, it can only support 1,500 Newton meters of torque, regardless of the direction. So the maximum magnitude of the moment about point A is 1,500 Newton meters, regardless of what's causing it. 1,500 Newton meters is the max. So we're told somebody put the rope onto the rod at point B, the rope is attached to point C, and someone's yanking on the rope. We're establishing tension in the rope. So we've got a force that is in the line of action of the physical orientation of the rope, and someone wants to say, okay, I'm increasing the tension on that rope. What force or tension on that rope is the max that I can apply before I exceed this 1,500 Newton meters? Now, in reality, we'd put a big safety factor on that probably. We'd want to stop way short of whatever force would end up giving us 1,500, but we'd want to find out what that max force is to give us a starting point. So this is a perfect way to apply our R cross F definition of moment. So I'm going to scroll down through. I'm not writing this problem out from scratch because there's a lot of writing and it makes for a busy whiteboard. So I've written out what is more or less a clean copy, and checked it, error checked it, and so I'm just going to step through what I did. So we're going to define the moment here of force F about point A, and of course this is a vector quantity, is of course equal to, by the definition of moments, the radius vector from point A to the point of application of the force at B. Well, we'll go back and look at that at our diagram. So there's B. So the radius vector is going to, let's see if we can draw here. The radius vector will go from point A to point B. And of course we have the force is a vector, and we know that the force is going to act along this line of action. Between B and C. We'll put that in blue there so you can see it. So we have two vectors. If we take the cross product of those two vectors, then we'll get the full vector expression for the moment. And from that, we can take the magnitude of that vector and set it equal to what we were given, and then back out the actual magnitude of f. So the first thing we're going to need are vector expressions for the radius AB and the actual force vector, whose magnitude we don't know, but we know what direction it's going. It's going down a line from B to C, point B to point C. So one way of saying that is our force vector is its magnitude f, which is going to be in newtons, times the unit vector BC, and we can get the unit vector by taking the full length vector, position vector BC, and dividing it by its length. So we're going to start with that. So we're going to define vector BC, and we can do that by subtracting the coordinates for point C from the coordinates for point B, and for that we have to go back to our diagram and do a little geometry. Point C is pretty easy. Our x coordinate is 6 meters because we went out 6, and our y coordinate is 6, and of course our k coordinate is 0 because it's just in the ij plane at k equals 0. B is a little trickier. We have to use our theta and r. So if we go up to a point that's equal to r times cosine theta, that'll give us our k component. And if we go over a quantity of r times sine theta, we'll get our y component, or j hat component. There is no I hat component for vector, or for position of point B. It's 0. It's I hat is effectively a coordinate is 0. So here we have point C, 6 meters, 6 meters, 0. And then for point B, we've got 0 meters. And then we have 4 meters sine 45, and then 4 meters cosine 45. These two obviously are going to be the same. If that theta had been anything other than 45, they'd be different. So we can subtract these from one another and then assign unit vectors for which direction they correspond to, and we get our full position vector that would take us from point B to point C, 6 meters I hat, and then 6 meters minus 4 meters sine 45 j hat, plus negative, because it's going down, 4 meters cosine 45 k hat. And just for simplicity of writing, we're going to turn those into numbers and chop it at 3 decimal places. So 6 meters, 3.172, 2.82 meters, negative. And we can divide this, we can first get a length, square each one of these terms and take the square root. That gives us 7.353 meters, which is the length of vector BC, and divide each of these terms by the 7.353 meters, and we get unit vector BC here, which is of course unitless. So if we multiply this by magnitude f, up here, we would get the full force vector. And of course, f is going to be what we're going to be solving for. So we need to go through a little bit more geometry to get our radius vector from point A to point B, which we're going to use in our moment calculation. So to go from point A to point B, we would travel positive 4 meters sine theta, which is 4 meters sine 45 in the y direction, and then down we would have to travel an amount equal to our 4 meters, which corresponds to the coordinate of point A, minus 4 meters cosine theta, which is this portion, which corresponds to the end of B. And so that gives us a radius vector of 2.82 meters in the y direction, or j hat direction, minus 1.72 meters in the k hat direction. So now we have what we need to crank through the cross product. We're gonna cross our RAB, which is in meters, into our BC, which is unitless, which we know is going to be multiplied by a scalar quantity F corresponding to the magnitude of our force. So we're going to actually do our R cross F. So I've done this with the FOIL method. So if you do the, going from first, inner, outer, last, and acknowledging the fact that our J hat cross J hat and our K hat cross K hat are 0, we end up multiplying out our terms in meters. And then, of course, J hat cross I hat is negative K hat. J hat cross K hat is positive I hat. K hat cross I hat is positive J hat. And then K hat cross J hat is negative I hat. And then, of course, the scalar negative positives follow. Collect terms. There's two terms going in the I hat direction. The other is only one term. And we end up with a total expression, which if we multiply by our scalar magnitude of the force, is the vector expression for the moment. So we could represent this actually up on our diagram. If we wanted to draw this, we can represent moment, assuming it's going in this direction. We can represent it either as a double arrow. Maybe we won't. We'll just describe that later. Moment is typically described as an arrow with a kind of a clockwise, counterclockwise circle around it, indicating what direction something would rotate around it, or a double-headed arrow, similar to a force arrow, except with two heads. And in both cases, the axis of the moment arrow is intended to indicate the axis around which the body or system would rotate. So it's just a convention for moment, which our screen won't allow us to show easily. So this is a vector, but it contains within it an expression for the magnitude of the force that we can safely yank on the rope. So we're almost home free. We were given the magnitude of the moment that we could support, which was 1,500 Newton meters. So now we need to get a magnitude for this. Well, that's easy. We know how to calculate the magnitude of a vector. We're just going to square all these terms, take the square root, add them up, take square root. And in that case, we can basically factor the f out, bring it over to one side ahead of time, so to simplify. So that ends up giving us the magnitude of the moment vector divided by the magnitude of the force is going to be 2.5648 and change meters. So that means the magnitude of the moment is the magnitude of the force times that same number of meters, which we were told can be no more than 1,500 Newton meters. So by algebra, we can solve for the maximum force as being 585 newtons. So key concepts: lots of use of vector magnitudes to relate what we didn't know to what we needed to know. We got to execute our cross product to actually calculate the vector moment from the radius from the point of interest to the point of application of the force, and an actual force vector. And we got a little practice using some geometry and trig to calculate a radius vector. And then we got some practice using a force line of action defined by two known points on the line. And again, our unit vector calculation method to determine a direction for a force independent of that force magnitude. So that is it for this example of a way to use our definition of moment about a point and everything we have learned about vectors, vector algebra, and the cross product to find something important about the corresponding force to create that moment. And that's it.